You get left in a lecture theatre one night after falling asleep whilst slumped down low on a seat. Your predicament is detected by a passing alien spaceship that beams down an alien robot. When it materialises in the lecture theatre, it wakes you up. And it proceeds to communicate to you by showing you this film. This is going to blow your mind. There are supposedly many clearly defined problems in our universe that are fundamentally unknowable. They're all equivalent to the granddaddy of unknowable problems, which is known as the halting problem, and for which there's a simple proof that we can't design a program or machine to examine another program or machine with its input data and tell us if it will complete nicely or go into an inescapable loop. This is supposedly impossible. But at least one renowned professor has denounced the proof as being ill-conceived and ill-defined. What if we were only to consider programs containing loops that we know how to detect? Strangely, we could construct the same proof inside this domain. And since we know we can detect these loops, then the proof must be wrong, but weirdly, the proof still gets accepted. It's just mind-blowing. We're going to explain the halting problem and the simple proof, analyse it, and consider a counter-argument. We'll go through Wikipedia's sketch of a rigorous proof. We'll go through the main argument in Alan Turing's 1936 paper. And we'll cover the relevant history, including discoveries in ancient Greece, infinities of different sizes, Gödel Incompleteness, and more. The mind-blowing proof is accepted the world over. And so, in order to be as detached and independent as possible, we'll contemplate what a highly logical alien robot from another world might say. After all, an alien robot might be quick to reject the logic that most humans find acceptable. So prepare to go on another journey of discovery and disbelief on the Karmapini channel. Karmapini. Any computer program with given input data must either finish nicely and stop, or else go into an inescapable loop, whereupon we might resort to switching the computer off and on again. It would be nice to have a way to know beforehand if the software is bound to go into a loop, but can we do this? The question is, could we build a halt or loop decider, which would take as input the description of any program together with its input, and determine if that program would finish running or continue to run endlessly? Or might this be impossible? The halting problem is attributed to Alan Turing, even though the expression halting problem was not coined until 4 years after Turing's death. It was attributed to Turing retrospectively, because his 1936 undecidability proof was considered to be equivalent to the halting problem proof. For that proof, he created a model of computation that we now call a Turing machine. Today, the halting problem proof is usually described in terms of modern programming languages. First, we assume that the decider functionality can be developed, and that this equates to getting a return value from a call to a programming language function. Next, we build a program that should always do the opposite of what the decider functionality says. This opposite program contains a lot of self-reference, since it asks the decider functionality to decide what it itself would do. If the decider says it will halt, it will loop, and if the decider says it will loop, then it will halt. So it seems like this opposite program will always contradict what the decider says. And so the third and final part of the proof is to conclude that since we could always contradict the output of a decider, then a decider can't possibly exist, And that is the proof in a nutshell. But this argument doesn't work if the decider functionality ends in a way so as to prevent any further processing. It could update the memory location of the variable called result, and then it could stop in a way that prevents the further processing that would contradict its output. And so the validity of the proof relies entirely on the ability to build a properly working opposite program, and it seems like this could be in doubt. One of the weirdest things about the proof is that it doesn't involve any loops that are undetectable. When it does the opposite to a halt decision and goes into a loop, it can be an easily detectable simple loop. And if it gets into a recursive loop when it calls the decider, then we know how to detect that kind of loop as well, albeit during runtime. If we can detect these loop types, then how the heck can the proof work? It seems like it must be invalid, and yet bizarrely it is still accepted globally as being a valid proof. The core logic of the proof is not restricted to just being about halting and looping. It can be applied to any non-trivial thing that a program could do, and this is known as Rice's theorem. For example, consider programs that always end after printing the letter H or the letter L. These could stand for high and low and so have nothing to do with halting and looping. The decider would be trivial in this case, as it could simply execute its input program with its input data. You might think that it should be easy to construct the opposite program, but if we dry run this logic, then it soon becomes apparent that it would hit a recursive loop. In order to ensure that it doesn't loop, we could trap the error and report an error message such as recursive loop detected. But this would introduce a third category of terminating, and so yet again the opposite program would not fit the requirement of halting after printing H or L. Notice that when we encounter a runtime error, it usually halts in a way that prevents any further processing from taking place. Similarly, a long-running program might be configured to shut down the computer upon completion, and this is another scenario in which halt means stop and prevent any further processing. But does it really make any difference to the core functionality of a section of code if it ends with one of these stop processing types of halt commands, or not? Normally, it wouldn't matter, but in cases involving self-reference, it could easily change the functionality. A very simple example would be some functionality that outputs whether or not its own code ends with a halt instruction. And so whereas we might group all types of looping together, when we talk about halting, we should distinguish between a halt that prevents further processing and ones where we call it halting, but we simply drop out of the code, and so we don't really stop or prevent any further processing at all. In the halting problem, these three categories are discussed as being just two, halt and loop. So going back to the H and L example, we could change the runtime error message to simply be output the letter H. We would then return to just having two categories, and the opposite program would then fit the criteria of halting after printing H or L. But the decider functionality would say that the opposite program will halt, and it would not be able to contradict that decision. And this casts doubt on the validity of Rice's theorem. Going back to halting and looping, we could take the different categories into account as we try to sketch the logic of a halt or loop decider. We could ask if the input program would try to execute an accurate version of this decider program or functionality. If it would, then we know this logic is going to be followed, and so we can predict a halt and then perform a halt in the safe knowledge that this is what's going to happen. This means it will never get to the code that tries to contradict the decider. So in this situation, the decider always wins. Critics might point out that we would still need to implement some highly complicated loop detection logic, and that it could be very tricky to determine if the input program accurately executes the decider logic. But the core logic of the opposite program is still defeated because it should still work even if the decider can figure out that opposite will accurately execute the decider logic. However, if opposite were to somehow simulate the decider logic instead of executing it directly, then could there still be a way that opposite could contradict the decider? If we design the opposite program to use simulation, and we assume that the decider program works by doing some very clever stuff, then when we think hard about what needs to take place, it appears that the process will end up in a recursive loop. This messy situation could be simplified if we could somehow remove the recursion from the scenario. And in fact, we can do this. Any functionality that typically uses recursion can be implemented using loops instead. So we could remove the recursion by having a programming language with built-in error detection that would halt with a runtime error whenever recursion is attempted. So an error should occur if the same routine reoccurs in the current nest of calls, even if the routine is inside a simulation. But to ensure this doesn't create a third category, the runtime error could simply print H and then halt, so that it matches what the decider would do when the decider's decision is halt. This way, we can create a scenario in which the decider functionality is trivial and will obviously work. We'll only consider programs that print either H or L, and then end by simply having no more code or by executing a proper halt instruction. This will unravel the logic of the halting problem proof, because with the aforementioned recursion detection, it means that all the decider needs to do is to execute its input program with its input data. In this scenario, when we try to make an opposite program that will contradict decider, it's the same as saying that it would need to contradict itself. If by some clever processing the simulation manages to avoid recursion, then the best it could do would be to find another way to loop, in which case it would no longer meet the specification of programs that print H or L and then halt. Indeed, the argument would then appear to be that however decider is written, we can always write a program that would force it to loop. This would be a complete departure from the original logic. It would never be able to reach the code where it contradicts the decider, and so that code would be redundant. It would then have to describe a type of looping that is 100% undetectable, and provably so. Since this would be a departure from the original argument, we can safely say that the original argument has been debunked, as it doesn't stand up to scrutiny. These results appear to conflict with the Church-Turing thesis that claims that any process can be simulated by a universal computing device. Again, it seems like this idea has been debunked. But perhaps we've missed something crucial that's only present in the more rigorous version of the proof. So we'll go through Wikipedia's sketch of the rigorous proof. It uses a table to illustrate the proof in which the ascending counting numbers each correspond to programs. It's easy to appreciate that counting numbers can be converted to computer programs and vice versa. We could just combine all the character codes of the symbols that make up a computer program and treat them as one very large counting number. And so it is possible to argue that computer programs and counting numbers are interchangeable. In the table, each column value corresponds to the ith possible program in a particular model of computation. The row values are also ascending counting numbers and represent inputs to the programs. The cells contain a 1 if that program plus data combination would halt, and they contain a 0 if it would loop. We can just focus on the diagonal values, each of which correspond to what a decider program should output when given an input program, together with a copy of that same input program as its data. The function g with input I represents the functionality of the opposite program. But the way its output is represented on the Wikipedia page can easily create confusion. Where decider says it will halt, the opposite program should loop, but this is represented by a U for undefined. And where decider says it will loop, the opposite program should print a 0 character and then halt. And so instead of using a 1 and 0 to represent if the function will halt or loop, instead they have used 0 and U to convey whether or not the function will produce some output. Now, since the I values represent programs that take one input, the decider program itself will not appear in the table since it takes 2 inputs. But at some point the opposite program should appear in the table. And when it does, what will decider say should go in the diagonal position where opposite is given itself as input? Well, as we've seen before, the functionality of the opposite program should always contradict the decider. And so this is exactly the same argument as before, except that now we've buried it in a lot of extra stuff about converting numbers to programs and going down a diagonal, all of which seem completely superfluous, as none of it seems to add anything to the argument. And so where has all this mysterious extra stuff come from? Well, it's all connected to the history of real numbers, and how they lead to concepts like an infinitely divisible number line or continuum, and the bizarre notion of infinities of different sizes. And if there's a problem with the halting problem proof, then it could shatter the very foundations of mathematics itself. The story of real numbers goes back to around 500 years BC, when the ancient Greeks found that the square root of 2 could not be expressed as a rational value. We are not sure who exactly made the discovery, although it's usually attributed to one of the Pythagoreans. They described the problem in terms of incommensurable lengths. The proof could have been interpreted as evidence that such lengths can't exist, since they can't evaluate to a constant. But instead they accepted that since perfect shapes must exist, these strange irrational lengths must also exist somehow. An equivalent modern day proof could start by assuming that the conversion of the square root of 2 into decimal form will reach an endpoint and give us a constant finite decimal as our answer. Then, by equating the square root of 2 to some rational a over b and squaring and rearranging, we can produce an argument that a over b is irreducible, upon which we could re-examine our initial assumption. And an alien robot might claim the most obvious conclusion is that we were wrong to assume the square root of 2 would evaluate to a constant value. But instead, the ancient Greeks assumed that it must somehow weirdly produce a constant. They simply presumed they must have discovered a new type of constant, and that this was knowledge that was previously only known to the gods. And legend has it that the Pythagorean Hippasus was drowned as punishment for revealing the secret. We can all appreciate that at a low level of detail or high pixelation, it's difficult to construct a recognisable right-angled triangle. At a higher resolution, the triangle shape can appear to be perfect. And in this way, humans can easily be convinced that they can imagine lengths of exactly the square root of 2. But an alien robot might object and claim that even when we imagine a shape in high resolution, it's still pixelated, it's just that the pixels are not that obvious. Could humans be wrong about their imagining of perfection? Perhaps instead of saying the length is exactly the square root of 2, we could say that as we increase granularity, it will match more of the leading digits produced by a square root of 2 function. Humans love to believe that they can conceive of completed infinities, but can our finite minds really do this? Not only did Plato think we could, but he described how this could happen. The external world is the first realm. Our consciousness is the second realm, and it allows us to connect to the third realm containing perfect forms. This was exacerbated in Euclid's Elements that started with the cringeworthy contradiction that a point is essentially a thing that is not a thing. And it established the axiomatic approach whereby the foundations can be pure make-believe rather than being evidence-based like a science. An alien robot might ask, "What is wrong with you people?" As if these absurdities weren't enough, just ask yourself, if a line goes from point 0 to point 1, then are the points 0 and 1 included in the line or excluded? Mathematicians will tell you that you can represent the line as an interval from 0 to 1, and if you use a square bracket on one side, it means the endpoint is included, whereas a rounded bracket means the endpoint is excluded. But an alien robot might point out that this leads to the absurdities that the empty interval and the interval of all real numbers must both be open and closed at the same time. But humans just laugh off these things as being peculiarities or quirks or just weird things that they've discovered as opposed to being real problems. The absurdities continue with the last part contradiction, or the end of infinity contradiction. Consider each non-zero base 10 decimal digit in the so-called infinite expansion of the square root of 2. We might claim the 1 can be represented as the line that is the half-open interval from 0 to 1 that excludes the point 1. Then the 4/10 digit could be represented as the line that is the half-open interval from 1 to 1.4 that excludes the point 1.4. And in theory we could continue doing this for the next digit, and indeed for all of the infinitely many trailing digits. And finally, we could add an extra line that is the half-open interval from the square root of 2 to the point 2 that excludes the point 2. The problem is what happens at the end of the infinitely many line segments or intervals. All of them supposedly exist in a static and unchanging state. There is no ongoing process here where the end bit is somehow changing. Every line segment or interval after the first must be preceded by a single line segment or interval, because they are all in order, one after another, with no overlapping points. Hence there must be a single line segment or interval before the final one from the square root of 2 to 2. So the concept of infinitely many is clearly invalid, as it leads to contradiction, as there is not supposed to be a last part to the infinitely many parts. Again, an alien robot might ask, "What is wrong with you people?" In 1594, Simon Stevin claimed that unending decimals could be used to represent any number, rational or irrational, and so the concept of real numbers as infinite decimals was born. And in the 17th century, calculus was devised. In differential calculus, instantaneous rate of change seems to imply that a divide by 0 should be possible. And in integral calculus, it appears that infinitely many rectangles, each with 0 area, can somehow together form a non-zero area. One way to avoid these absurdities would be to relate real numbers to algorithms or computer programs. Indeed, this is what several eminent mathematicians did, including Jules Ricard, Alan Turing, and more recently Dr. Doron Zeilberger, who called pi an equivalence class of algorithms. In the same fashion, the square root of 2 would simply refer to any algorithm or program that would try to execute the square root operator on the number 2 to produce an answer in decimal form. The real number refers to the algorithm specification itself. It does not refer to any attempt to perform or execute the algorithm. This would mean that a real number represents a type of algorithm rather than a constant value, and so strictly it should not be called a number. As such, it would no longer need to be an actually completed infinite sum of non-zero terms. It took several decades in the 19th century for some of the world's top mathematicians to devise the arguments that support the notion of real numbers as limits. Maybe it took so long because it was new and it seemed to contradict common sense. For example, the series 1 plus 2 plus 4 plus 8 and so on clearly can't sum to a constant. In order to sum to a constant, its trailing terms would need to all be zeros, and we can prove that the nth term can't possibly have a zero value. But then, what about the series 1 plus a half plus a quarter and so on? We could prove that this can't become a constant in exactly the same way. But in base 2, this series equals an infinite decimal. And to a mathematician, these must represent constant values, and so they convinced themselves that it's valid to say the increasing sum tends towards a constant value that they called the limit. This limit argument allowed them to claim that some infinite sums could have a finite decimal representation, and that the limit could be found without having to traverse the entire infinite sequence. But others, like the square root of 2, couldn't, and so there was still no way to avoid the bizarre notion of a completed infinity of decimal places. Worse still, some series were found to converge to different values, or even diverge when the terms were simply rearranged in a different order. True to form, mathematicians denied that this was a problem, and proclaimed that it was something new that they had discovered, and weren't they so clever to have discovered this? But if you were given any conditionally convergent series to start with, then you could use it to make any series conditionally convergent. Even one as simple as 0 plus 0 plus 0 and so on. We simply add and subtract each term of the conditionally convergent series with its corresponding term in the supposedly well-behaved series. 1/2 of the added terms forms the original conditionally convergent series, and the other added terms form its negation, which is also conditionally convergent. And since these two series that we've added can converge to different values, it means our original series can't be trusted. And by extension, no infinite series at all can be trusted to converge properly. An alien robot might think that this completely trashes the idea of limits, and yet again highlights the absurdity of believing that infinitely many is a coherent concept. But no, we clever humans easily batted away this problem, as we did with every other problem, by saying you're simply not allowed to do anything that would cause a contradiction. Therefore, there is no contradiction. With superior logic like this, the alien doesn't stand a chance. Even so, the alien might still disagree with our logic. The alien might form the opinion that instead of rejecting infinity, mathematicians had gone so far down the infinity rabbit hole that there was no way back. So they were just papering over the cracks with ever more clever sounding arguments, their so-called discoveries, and their made-up restricted rules. But these clever discoveries concerning real numbers got even weirder, as we can see when we examine the key events leading up to the halting problem. One of the weirdest ideas was that there were infinities of different sizes. This was proposed in the late 19th century by Georg Cantor. Cantor's diagonalization argument has some similarities with Turing's proof, since Turing also uses a similar diagonal in his paper. Cantor used a method of one-to-one correspondence to supposedly compare the sizes of different infinite sets. Weirdly, he concluded that the infinite set of real numbers was a bigger kind of infinity than that of the natural numbers. He used infinite strings of ones and zeros that he related to real numbers. But the notion of infinite sets led to self-referential contradictions that once again had to be dealt with by saying, you're not allowed to construct any sets that lead to contradiction. The strings of ones and zeros were unending strings and not base 2 decimal representations. He pointed out that if all the strings could be listed in some order, then it should be possible to construct a new string containing the opposite digits to those in the diagonal. This new value is sometimes called an anti-diagonal, and it would contradict the starting assumption that all possible strings could be listed. But instead of concluding that completed infinities are obviously not possible, he concluded that real numbers were uncountable, and that there must exist infinities of different sizes. Russell's paradox was dealt with by saying, you're not allowed to do that. And then in 1905, French mathematician Jules Ricard produced an interesting paradox. He suggested that real numbers could be unambiguously defined using natural language, and so 17.101010 etc. might be defined as a real number, the integer part of which is 17, and the nth decimal place of which is 0 if n is even, and 1 if n is odd. This would allow the real numbers to be ordered based on length and then alphabetically within equal lengths, giving a list of real numbers R1, R2 and so on. Mathematicians were worried that this might be the final nail in the coffin for Cantor's highly controversial arguments. Ricard continued with a statement that corresponded to Cantor's all-important anti-diagonal. The statement would attempt to construct a new real number by changing digits in the diagonal of the list of real numbers. The question is, should this description of the anti-diagonal appear in the list of real numbers or not? If it was in the list, then eventually it would attempt to process itself. And since we have deliberately not specified what its own digit should be in this case, then it will fail to produce the infinite diagonal. This means that if it is in the list of infinite real numbers, then it should not be in the list of real numbers. Whereas if we say it is not in the list, then it won't hit the problem of having to process itself. And since it won't hit any problems, then it should be in the list. This is equivalent logic to Turing's proof of undecidability. This appears to highlight two very important issues: a possible one-to-one mapping of real numbers to natural numbers, and that any attempt to construct Cantor's anti-diagonal value would lead to contradiction, which would leave Cantor's diagonal argument completely in tatters. But Ricard didn't claim these things, and instead he suggested that his definition was probably invalid for some reason, such as not meeting the criteria for valid descriptions of real numbers. For example, if the criteria stated that you were not allowed to process a list of all real numbers, then his statement matching Cantor's anti-diagonal would not meet the criteria. Contemporary mathematicians also agreed that Ricard's definition was invalid, but for a different reason. They said there's no well-defined notion of when an English phrase defines a real number. But this was still a problem for mathematicians, as they would need to create a counter-argument for when real numbers were specified mathematically rather than in English. This problem was solved 7 years later when Émile Borel devised the concept of a computable real number. A real number is considered to be computable if we can devise an algorithm that could calculate its nth digit. Now, the traditional meaning of the word computable is capable of being calculated to completion. And so, to say that pi and the square root of 2 are computable could be construed as a tad misleading. And then, 16 years later, in 1928, the influential German mathematician David Hilbert challenged the world's leading mathematicians to answer questions such as, is mathematics complete? Is mathematics consistent? And is mathematics decidable? Kurt Gödel provided answers in the negative for the first and the second of these questions. And then independently, Alonzo Church and Alan Turing both replied no to the third question. Next, we'll do a quick summary of Gödel's first incompleteness theorem. Gödel started by devising a way to convert mathematical statements to numbers. Each symbol would have a unique value, and each increasing prime number would be raised to the power of each symbol's numeric value. With no negative numbers, we might have an axiom that says the successor of x cannot equal 0. Then if we substitute 41 for x, we can make the statement that the successor of 41 is not equal to 0. Taken together, these two statements are considered to form a proof that 42 does not equal 0. And if we raise 2 to the power of the axiom's Gödel number and 3 to the power of the other statement's Gödel number, we can calculate a single Gödel number for the whole proof. These numbers would be huge, and so to convert back from a number to statements would be virtually impossible. In today's world of computer programs, an easier way to convert between statements and raw numbers could be to use ASCII character codes, for example. The whole point of creating this Gödel numbering system was so that Gödel could encode a version of the infamous liar's paradox in a purely mathematical setting. And so at the heart of Gödel's argument was the statement that there is no proof of this statement. The logic is that if a proof did exist, then the statement would be false, which would form a contradiction, and would mean that the mathematical system could contain inconsistencies. But if a proof did not exist, it was seen as proving that some statements could never be proven, meaning the mathematical system would be incomplete. But with statements like the liar's paradox, there's a lot of controversy about what being true or valid actually refers to. If we compare Gödel's statement with a statement like, there is no proof that this statement is grammatically correct, then we might realise that being true or valid has to refer to some specific thing, otherwise the statement is meaningless. Consider a statement that is pure gobbledygook. It can't be classified as being true or false. It requires a third option of meaningless or incoherent. So whereas we can check if a sentence is grammatically correct, we can't check if there is a proof for Gödel's statement, because Gödel's statement is meaningless or incoherent. But yet again, mathematicians don't seem bothered by these issues, which is not surprising since they readily accept that the whole of mathematics is simply a game of fiction. The liar's paradox concerns the sentence, "This sentence is a lie," which seems to be paradoxical. The trick is that we are fooled into accepting that the sentence must be one of the two options, a lie or not a lie. But once we realise that calling it either of these two things would not actually have any coherent meaning, then we can avoid being tricked by realising there's a third possibility, which in this case is the category of meaningless or incoherent. Alonzo Church's 1936 undecidability proof using his lambda calculus was considered to be equivalent to Alan Turing's proof of the same year, which was in the days before recognisable electronic computers existed. At the time, a popular model of computation came in the form of finite state machines. Such a machine might parse input strings so that valid strings could be accepted and invalid strings could be rejected. A final state or halt state would typically relate to the point at which a string was accepted or rejected. But even if we label a final state as halt, it doesn't mean the machine will stop. It will stop processing that particular string, such as by accepting it, but it will happily continue to process other strings. We could even have a machine where every state is a final or halt state. It doesn't mean that processing of an input string will stop on the first state. It just means there's a possibility that processing could end on any particular state. An empty string might end at the first state, a one-character string might end at the second state, and a two-character string might terminate at the third state, whereupon they will be accepted if they meet the criteria. In this context, the word halt is just a label. It is certainly not a machine shutdown instruction. The processing of more input was par for the course immediately after a halt state had occurred. And now we come to Turing's paper itself. Turing was happy to relate real numbers to infinite strings of ones and zeros, as Cantor had done before him. In the introduction to his paper, Turing makes it abundantly clear that the paper is about computable numbers and computable functions. In the paper, he describes how integers could be converted to program code, and that some of these programs would, when executed, print ones and zeros endlessly, which would then correspond to one of Cantor's infinite strings, which in turn could be related to a real number. And so this was at the heart of Turing's undecidability argument. It was concerned with programs that print endless ones and zeros versus programs that don't print endless ones and zeros. It wasn't concerned with halting or looping. Turing's argument went like this. We go through each positive integer, convert it to a program, and then check if it would print ones and zeros endlessly. If it would, then we should accept it, otherwise we should reject it. Now, the objective of this algorithm or program is to output ones and zeros that correspond to the diagonal in Cantor's diagonal argument. And so for the first program converted from a positive integer that we accept, we should simulate it up to the point where it outputs its first digit, and then we should use that digit as our output from this program. For the second accepted number or program, we should simulate it up to its second output digit, and then we should use that as our output from our program, and so on. The problem is that if this program itself corresponds to the nth accepted positive integer, then it will end up in a loop when it tries to simulate itself in order to determine its own nth output digit. We could fix this by forcing it to output a 1 or 0 when it encounters its own number. But for Turing's proof to work, we want it to fail at this point. Because then we can say that if we decided to accept this program as one that prints ones and zeros endlessly, then we would have been wrong. And if we had rejected this program, then it would not have hit the problem of processing itself, and so it would print endless digits, and so it should have been accepted. And so whether to accept or reject it would appear to be undecidable, since either option would lead to contradiction. We can simplify Turing's argument even further if we assume that this main program just happens to be the first one to be accepted or rejected. Then we can focus on how it processes itself at the start of the code, instead of being distracted by its processing of other programs. If it decides that itself will print ones and zeros endlessly, then it will end up in a loop of endlessly starting a simulation. So it would not print endless ones and zeros, meaning that the decision would have been wrong. But if it decides that it won't print ones and zeros endlessly, then it will go down to the part of the code where it will print ones and zeros endlessly, because this is where it will process other positive integers / programs. And so again, the decision would have been wrong. And this, in a nutshell, is a neat and simple way to represent Turing's undecidability proof. Even though Turing's argument was not about halting, it adopted the same type of logic that was used in the other halting-related proofs that we've examined. And in all cases, the logic doesn't work if the decider ends by halting in a way that prevents further processing. And so for the scenario in Turing's paper, when it is processing its own number/program, it should decide that it will not print endless ones and zeros, and then it should halt properly, thereby preventing this decision from being contradicted. In all cases, it is the opposite program or contradiction that cannot occur. There is nothing to prevent the decider from existing. So these are all just variations of exactly the same argument, and they are all susceptible to the same counterargument. The terminology used in Turing's paper can be quite confusing. He distinguishes between printing other symbols and what he calls symbols of the first kind, which he defines as consisting entirely of 0 and 1 symbols. And if a particular machine or program endlessly prints symbols consisting of zeros and ones, then these machines or programs are called circular. Programs that do anything else are called circle-free. This can be confusing because these terms are not in any way talking about looping versus not looping. A circle-free machine or program could still print symbols endlessly, it's just that they would not be exclusively ones and zeros. In relation to converting between positive integers and programs or machines, Turing called such a number the description number, or d.n, of the machine. We might think of the description number as being converted into some modern day program code, but Turing's equivalent to this was a string of characters that is referred to in the paper as s.d. The job of the decider functionality is then to decide if the code it is presented with would endlessly print ones and zeros. If it would, then the corresponding description number can be called satisfactory. Note that the functionality we've been calling opposite is referred to as h in Turing's paper. Here, h is just a convenient letter to use. It doesn't have any meaning related to halting. Turing uses the letter d for the decider functionality, and as a result of the apparent contradiction, he concludes that there can be no machine D. We've already talked about Rice's theorem and when the expression halting problem was coined, and so we've reached the end of this journey. A critical alien robot might still not be happy with our logic, but unlike them, we humans will indoctrinate all future generations with the truth that mathematical proofs are right forever and can't ever be contested by alien robots or anyone else for that matter. Other mathematics and even things in science depend on these proofs that have been devised and accepted by generations of the cleverest humans ever to have lived. And so if some random nobody dares to question these things, we should probably remind them that their opinions are worthless. Even if we happen to be the laughing stock of the universe, we won't care, because we know that we have the superior intellect. After all, we can conceive of and appreciate the nature of infinity itself. Unlike all of those that disagree and complain and obviously don't understand what they're talking about. If they understood anything, then they would accept what we keep telling them. And so it follows that all disbelievers of our mathematics must obviously have inferior brains. Moreover, our glorious approach to mathematics will remain intact, not debunked in any way, shape or form, and it will reign supreme forevermore. Aren't we the clever ones?